Really good to see you all. All of you have the post-lunch kind of blues. I'm going to try to do a demonstration today of how the internet really works using people as packets. And so far I've gotten 4 volunteers. I'm going to need 6 more at least. So if people can put their hands up, please volunteer to be a packet. It'll be fun. Oh, I got one more. Come sit in the front, please. Great. So I'm going to do an introduction to network congestion control, demonstrate how TCP and queuing actually work, why we have windowed protocols, and I'm ultimately going to get to this thing called bufferbloat. I've been involved in the internet since the early 80s. I'm almost 60 years old. I'd like to retire knowing that all of you know how the internet works. And in 1991, when I first started working on audio applications, my dream was to plug my guitar into a wall and play with my drummer across town because he never showed up for gigs. I never thought it would be as hard as it proved to be. I thought inside of a couple years we'd be able to just do that. The speed of light across town would be about 36 microseconds. Why was this impossible? Only during COVID we've invented techniques to make it possible to play with a drummer across town. So these days I run the Make Wi-Fi Fast project, as well as the Cake project for bufferbloat.net. I'm the chief science officer for a company called LibreQOS. And a lot of my outreach is really unpaid for, so if you're into donations, let me know. For the last 15 years, I have been working with a bunch of internet originals, all the way up to Vint Cerf, Jim Geddes, Eric Raymond, to try and rip all the extra latency and jitter out of the internet. This is a study done by the FCC about what's wrong with the internet. Who here has ever done a big upload and have their internet basically freeze? That's bufferbloat. You ever had a video conference go? A lot of times that's bufferbloat. It turns out that the idle latency for almost all of our technologies is actually quite nice for voice and video. But the instant that you start using it, at the 95th percentile, we see an inflation of 55 milliseconds here. I have a laser pointer in this? Yes, I do. Up to 790 at the 95th percentile. Almost 2 seconds at the 99th percentile, and maximizing at 3 seconds. Cable was similar, and Starlink was similar too. There's a simple test for bufferbloat. Try this one. Now, since we've been working on fixing this problem for over 15 years, a lot of technologies have emerged to make it possible that when you're doing your big upload or your big download, for your router to handle the problem for you. Algorithms have been called smart queue management, smart queues, SQM. They all use an algorithm called FQCODL, RFC8290, or CAKE. And if you Google for bufferbloat, that's the answer. Go out, get yourself a new router, and then you'll never have this problem again. That really wasn't the solution we wanted to have. We wanted to have the internet universally capable of handling voice and video, uploads and downloads simultaneously if we just got rid of the bufferbloat problem. Wanted the internet to be kind of like a book, you know? You know, it's really amazing. You do a download today, and then you click on something else. A book is actually still more performant than the internet is today. So I hope that we can, by deploying these algorithms, that will build a much more interactive, even a metaverse, internet. So the algorithms that we use are now being used in middle boxes throughout the WISP industry. The company I work for now is called LibreQOS. It just applies these algorithms, it gets us to where we go from 30 milliseconds of latency to 35, not seconds. And did a bit of work on Starlink. They listened. And they have set up their entire network to aim for stable 20 milliseconds worth of latency throughout their network. And I hope that all the ISPs in the world do the same. Because then we can have voice and video, gaming, ER, VR, anything coexist at the same time across the internet. But why do this problem exist? Going back to 1986, a fellow by the name of Van Jacobson. Who's here have heard of him? We owe a lot to Van. The very first internet in 1986 collapsed because we didn't understand that if you put packets into a pipe, they have to come out the other side at a different rate. This might be 100 gigabits, this might be 10. And you have to adapt, I'm not doing this well, the rate at which they come out in order to be able to get the data back out the other side. You see a lot of Wi-Fi networks today that are almost completely unusable in hotels, etc. Who here thinks that if a gigabit of bandwidth is enough? Wow, I got a silent audience. 10 gigabits. No? If you're at home, you should have a gigabit at home? If you had a gigabit at home at 1 second of latency, would that be good? No. Okay, so that's the point. If you have 10 megabits at home with milliseconds of latency, that will completely outperform a 10 gigabit link with 100. So this was old research, and this is why CDNs exist today, is we developed that the closer the data got to you, the faster you actually got it. Bandwidth has very little to do with it anymore. So rather than come up with ways of dealing with the buffer bloat problem, we've come up with, we've devolved the internet. You do a short download, you do a short upload. You have rate-limited streaming. Old applications that you do things like uploads and downloads, there. So I'm going to do a bunch of demos today, hopefully try to bring up the energy level in the room. So I've gotten 1, 2, 3, 4, 5 people to come up, 6. Can I get you all to stand over here for me? I could use 2 or 3 more people in the end. Oh, one more, great. Cool. And I had a Frisbee, there it is. All right, actually if we get you all to come up in a line right about to here for me. That's good. All right, that's a lot. I want to demonstrate what voice and video conferencing traffic looks like. Okay? What you want to do is make a wave for me and walk past at roughly the same steady rate. Okay? And then come back in the circle back that way. Wave, do a wave. No, I got it. Just keep going. Okay? Everything comes, you can go all the way back to, keep making a circle, guys. I have a couple demonstrations to make.
I want you to go back over
Go back this way. Go back that way. Unruly packets, they're hard to deal with. Okay? That's how voice and data, voice and video data actually comes out. It comes at a steady, constant rate. And you see each individual packet is packetizing each individual portion of that wave. If you sample at fast enough rate, it's invisible what's actually going on here. But if you transport packets across the internet, come on back, guys. All right? Do the wave. Here we are doing the wave, but all of a sudden we have a stop. And you get that moment. And then move fast. You might have it come by really fast. Okay? Stop. Sometimes you do a loss. And you have to interpolate what happened there. So, he's gone. There, you go faster forward. Okay? Thank you very much. Give a big hand for our packets. Get back in line now. Get back in line. That's cool. Now, voice and video come out at a constant, steady rate. Any interruption of the rate and delay on the rate, any loss of packets in the link is what causes your video conference to feel uncomfortable. You can also end up with a lot of delay on the link. So you might have someone talking, and that's typically a buffer bloat. The thing is that video conferencing came about quite a bit later than web traffic did. And I needed a glass of water real quick. So I'm going to talk about, why don't you come up a little forward here. Now you've got your typical web application today. Come forth. Thank you. I'd like to make a connection. Go tell that guy I need more data. Okay. Thank you for more data. Can you go tell that guy that I need more data? Go back in line. Great. And could you tell that young lady that I need more data? Okay. And tell that one I need more data. Okay. Now that is a very very simple, very close, short round trip time kind of network connection. The thing is that the internet is connected by a distance. And the TCP, let me get back to this. There we go. There we go. All right. So when you have a TCP connection, you actually have, might be the speed of light. It could be another machine in the cluster. It could be used on the other side. And TCP has a three-way handshake. So come to me, sir. I'm so glad to have a connection. Could you go back and tell them we're OK to transmit data? Yeah. That's a SYN. He sends a SYN ACK. That's so wonderful. I sent a SYN ACK back. Now, by the way, ACKs are really small. You go like this, and you crawl back there. And now you can do a GET request. This guy's a GET request. Come on, give me a GET request. All right. Great. I'm going to give you all this darn data now.
All right.
That's awesome. I need a couple more people out here. 4. Give me 4. Now, once that happens, you have to fill the pipe. You have this set of transactions like this. And then there's a thing called the initial window. There we go. Where IW10 is the current. But I only have 4 people out here, so we're going to have 4 people come out. So you 4 guys, stay where you are. Thank you. Send me that data. Freeze! All of you. Right there. Freeze. There you go. Now, these folks have filled the pipe. And that's what we want to do. The pipe can be of any length. And we don't know how big it is when we start. So give me 4 more packets out here. You guys stay frozen. Yeah, good. All right. Now, what happens, because we don't know that, stay here, since we don't know the distance of the pipe, how big it really is, each one of these packets is going to send out an ACK asking for 2 more. So you, sir, come. You, sir, come out, the ACK. Okay? 2 more are going to go. Okay? 2 over here. Come on. Move there. 2 more. All right. Another one of you guys. Another one of you guys. Look. Okay. 1 pack. Okay. 2 more. Go. Uh-oh. We're out of packets. I'm going to pretend to be one. All right. Now we're going to all freeze. And we've successfully filled the pipe. We've managed to take advantage of the speed of light to store data in it. The thing is that we don't know when to stop. We don't know when the distance, the speed of light is different from the amount of buffering. So if you guys were to come closer, pipe at the same time, stop. He's entered a buffer. Come closer. Keep coming, keep coming, keep coming, keep coming. Now, in my case, I've only got a 4-packet buffer, and I'm so sorry. There's no room for you in the queue. Just step aside for a moment. Rest of you come forward. Little ACK goes out. Little ACK goes out. Another ACK goes out. Another ACK goes out. Another ACK. Now this guy has noticed that she's not there anymore. And that ACK goes, come together. Come here with me. All right. Has told the server behind him to replace that packet and also slow down. It's called the TCP sawtooth. Oops. All right, all of you march slowly towards me and stay. Okay? Now, as each one of these, keep on, come on, you keep walking. Come on, this isn't the salt mines. Okay. Keep coming around. Now you're going to speed up a little bit. Okay? As you get more and more and more, you speed up. You turn around again, you speed up. Come on, do that. We're spending all the data we possibly can. And oh my God, we ran out of space in the queue. And we lost him. I'm sorry, man. It's okay. Keep going, come around. Okay? See this guy? Go back with him. All right? And at this point, and now we've seen this loss, we slow down again. Keep going. Just keep trying to fill the queue. Keep fill the pipe and not the queue. Now, I'm not going to go into congestion avoidance in this one, but this behavior, you guys can all come out. You can even sit down if you like. I know I need to. Thank you very much. I have more down. Don't leave me completely. I just have more. I got to take a break. This behavior is called the TCP sawtooth. It was more or less invented by Van Jacobson at the initial internet congestion collapse. And if the internet did not behave like this, where you constantly sped up and then the loss of a packet slowed down, it would not work today. So this is not a physically enforced behavior of the internet. It is a protocol. It is a mutual contract. Uh-oh. Pretty much everything has to work this way. Now, the remarkable thing about this idea is it works out to about 11 orders of magnitude, well past the moon. And it's stable for thousands upon thousands upon thousands, trillions of connections simultaneously through the entire internet. And back in 2006, 2008, we broke it. There's this thing called bufferbloat. Can I get my people back up again now you've got your rest? What if, instead of that really short buffer I showed you, controlling the speed up and down, that we made it be seconds long? So we're sending data. All of you guys come with me. Where's my stick? There it is. And that signal never arrives back at the TCP sender. What I've done right now is I run out of send. Keep coming, guys. We were talking about seconds of delay. What I've done in this demo right now is I run out of send window. You have to imagine the rest of you filling in that pipe there, sending ever more data, more and more data, following all this stuff, until one day, the signal from the sender reaches the other side, and you drop a packet. But with all this buffering here, we're trying to send stuff to the poor sender over here. Keep going. Back there. Keep going. Keep going. I'm going to keep picking on you. I just dropped her again. And all of this stuff here can no longer make it to the receiver, can no longer be processed by the receiver. So what we have to do is the next packet that notices that that packet was dropped have to go all the way around the room again to fill in that hole in the data. No, you guys are stuck. They've already been delivered. They're here, they're in the computer, but because that one poor missing packet have to wander through an incredibly buffer-bloated universe, you get that in your stream. All right, then you guys, and now that they're here, the data's been there, and they can go from there. Thank you so much for making that extra journey for me. I appreciate it. So, again, for stability, most TCPs will reduce the rate by a half on a packet loss and retransmit. When we started the bufferbloat project, the world record for buffering was 864 seconds, held by Viasat on their particular satellite network for telephones. We see 16 seconds on a lot of stuff. I've seen well over 40 seconds on cellular. The speed of light across town is 36 milliseconds. So coming up with a timely way of doing timely loss or marking is essential for the network's correct operation. Now, I get my cue out again. You all rested up this time? Come on out again. So you started that connection again. Keep going, keep going, keep going. All right, stop. Thank you. Now, there's no such thing as flow control on the internet. There's no signal to the sender that says to slow down or even continue. So what happens, come and turn around for me, is that it has what's called an ACK clock. ACKs are small. Okay? And if that ACK clock gets blocked, then we end up with the stream not being able to continue. Okay? So you have to worry about congestion on both the uplink and downlink portions of the system in order to be able to compromise. All right. So when you have these kinds of behaviors, when you grow up, everybody jump. There, that's cool. And you have something else that's trying to go like this. Come on, guys. Like this. You have a tech problem called riding the sawtooth. You develop a jitter buffer that is slightly larger than the actual height of the sawtooth. Ideally, that sawtooth height is short. 90 milliseconds would be good, 60 milliseconds. Not seconds! Okay? And what you see, however, is things like Zoom and all of our video conferencing tools today have hundreds and hundreds of milliseconds because of excessive buffering in the network today. So you guys can now go back that way. How am I doing for time? I didn't even look. Really? Oh boy, you guys are in trouble. Thank you. Thank you very much. Who here has already heard of fair queuing? Bigger hands, do it taller than me. Okay. Who here has heard of active queue management? Okay. Who here, before I came and talked about the TCP sawtooth, had heard of it before? This is the substructure of what all of your applications are running on all the time. And I would really like it before I retire if everybody in the room knew how it worked. The internet and many of your applications are full of what's called FIFO queues, first in, first out. Give me 4 people in a row here. Your typical Netflix flow might be, say, 20 packets at a time. Your typical VoIP flow will be a similar single packet. Give me one person in a different queue. You might have, stop. Good point, yeah. Great. I get you in a third queue, miss? Right there? That's great. If you have multiple queues and a way of multiplexing between them, you can take away the effect of the TCP sawtooth. Netflix will be going up and down trying to grab more bandwidth as I described, but a voice call will be sending 1 packet every 20 milliseconds. So what would happen in a classic fair queuing system is that this packet would go, stop, and then this packet would go. Okay, and this packet would go, and then that packet would go. And as this is happening really fast, the rest of you guys, being Netflix, stuff from there. Fair queuing is an old technique, 1989. Why it didn't become the default for the internet as a whole, I will never know. We developed an improvement to fair queuing called flow queuing in the FQ-COTL algorithm. I'm curious, who here has an Apple? Okay. How many, keep your hands up, how many here people use Linux? So it's pretty much the whole room. If you get a chance. The algorithm that actually touches nearly all the packets in almost all of your devices today is called FQ-COTL. It's a bit different. Netflix folk, can you, actually you guys just come forward. My 2 VoIP packets. Stop there, you come here. You're coming out every 40 milliseconds. Okay? Netflix, VoIP, Netflix, boom. Okay? VoIP. FQ-COTL takes the first packet that, I'm going to need one more VoIP packet come forward. You sir at the end. Thank you. I'm not doing this particularly well. Stop. But if the queue is empty for the VoIP packet, it will actually go out before the Netflix packet. So anytime you have a flow that is coming in at a rate that is less than the total of all the other flows, it automatically goes out first. Most of our traffic is very lightweight. Thank you, Mr. White. And you guys go back over there. My fight has been trying to get this particular algorithm running on the ISPs of the universe. Clocking, running a sawtooth, fair queuing, and keeping queues short. What happens when you walk into a store that's too busy? What do? Sometimes you turn around and walk out, right? Humans do that. Packets don't have enough knowledge to do that. They can measure time or queue occupancy. So a lot of different algorithms have been proposed to figure out a way to have the right size queue. What do you think the right size queue should be? Anybody? Any application, not just networking. Not bad. Anybody else? How big should a queue be?
Depends on the application.
That's a terrible answer. It depends. How many of you use queues in any of your work in regular code? I'm just curious. Yeah? How big should a queue be? I just heard infinite?
Or empty.
Empty. Anybody else? It's terrible. This is the fundamental structure in all of our network software today. 16. You use channels. You use queues. The ideal size for a queue should probably be less than 2 units of work. And the average utilization should be less than or equal to 1. And yet I find in a lot of code that I've looked at today that people just have an infinite queue. The code underneath it, just underlying it, just keeps allocating more and more memory. Another answer for queue length is it should be big enough. Anybody here use Uber? Yes? Uber applied the GOTO algorithm to decide when to drop requests coming in, particularly in their flooded situations. There's a thing called good queue and bad queue. You want to have just enough space to have an average utilization of roughly 1, and not so much as to add an infinite amount of delay. So I've been at this now since 2012. We have gotten this algorithm running on almost all the devices that you own, except the bloody routers. It's really a shame. You know, DSL has a wide reputation as being terrible, but it's terrible because it has really horrific queuing delay. And all you have to do is reflash a router with something like OpenWrt or DDWrt, and your DSL will get that much better. Similarly, people say, fiber. Well, fiber has about, and I actually saw a new record, Lumen. I'm going to pick on Lumen. Lumen had over 3 seconds of buffering on their 100 megabit service. I see buffering on all kinds of fiber. In this case, remember I talked about riding the TCP sawtooth? So your video conference on this particular piece of fiber would have an intrinsic amount of 60 milliseconds worth of delay because of the existing jitter. Or, using the cake algorithm, 0, 3 or 4 milliseconds total. It's my hope still to build an internet where you can plug your guitar into the wall and play with a drummer across town. This is the only way to get there. So we've written a lot on these particular issues. Probably one of the best ones is Jim Geddes, who's the founder of the effort. You can go out today, if you've had these kind of issues with your network, go out and get a router with SQM on it. I am hoping that now the solutions exist in very cheap middle boxes, that more ISPs will actually do the right things. Comcast has a different algorithm called L4S that they are deploying. It's going to be pretty good. And on the sender side, there's a whole bunch of other new algorithms, like who here uses BBR? Anyone? All you web developers, give that a shot. Just get FQ as well. And there's all kinds of great monitoring tools, which are not really the subject of this talk, but you can see me later, where you can pay attention to the amount of latency your applications are inducing. Now, almost every conference I go to, I measure the Wi-Fi. This was the last time I did this one. The Wi-Fi went from 10 milliseconds of delay when you weren't using it to over 1,400 milliseconds of delay. These are all solved by newer gear and newer equipment. So that's it. My company now has about 4 million devices under management with effectively a minimum of 24 milliseconds and 38 milliseconds tops under load, which finally will make it more possible for the metaverse to exist. Thank you very much for having me today, and thank you very much.
And thank you to our packages here.
Thank you. I guess we have some spare time.
What is UDP?
What is UDP? We're in the basic stuff. UDP was invented as a way of having a connectionless transport that was designed for real-time applications. It had no notion of a connection per se. You just blast it out and hope the receiver gets it.
So how would that look with our actors here?
I'm not sure if I understand.
If our 10 actors here should simulate UDP traffic, how would that look?
On this network?
Yeah.
I don't know. I have to go test. I did run a quick test. The Wi-Fi here was not bad. It was only about 200 milliseconds worth of jitter. So yeah, we got some time left over, guys.
The ACK packets would have gotten lost with UDP, so we would have pushed any number into the top, and only the one that dropped out would have come through. All the others would have been lost, right? So that makes horrible problems for loss. I mean, like most of the people, probably everybody would have been pushed over almost immediately.
Well, the first point I'm trying to make is that loss is a necessary aspect of the Internet's application. If we don't have it, you end up with bufferbloat. However, statistical loss is much better than bulk loss. So in the case of VoIP, for example, if I lost 2 packets out of 5 on a regular basis, you wouldn't be able to tell the difference. However, if you're using 2 packets out of 5 for TCP, your throughput would be very, very minimal. Now, in part of the bufferbloat effort, we've actually, anyone ever heard of ECN? No? Explicit congestion notification. That allows you to do congestion control without actually having loss with a smart algorithm like Pi or FQCODL in the way. And you can turn it on tomorrow if you wanted to. The L4S project, which I mentioned earlier, Comcast and Cable Labs driven, uses ECN to give you a high priority, very low latency queue, but does it without any packet loss. Now, what is that going to mean for VoIP and video applications? They're just barely beginning to deploy it. But I do encourage people to play with L4S and ECN. More questions?
What is a remote direct memory operation network?
Oh, man. Now you're getting really, really, I'm mostly focused on the edge here. You're talking about RDMA. So there's, the classic internet is structured today with the kind of congestion controls that we use. InfiniBand and RDMA uses a credit-based system to make sure that they never oversaturate the media, and it's only a short distance protocol. You can't get it outside the data center.
Thank you.
We got more?
Could you go into a little more detail about why you're unable to get the algorithms on the routers themselves?
I'm not unable to. I'm trying to convince people to install their own firmware. So we have the Wi-Fi marketplace in particular. Every year there's a new Wi-Fi standard, and every year people get more Wi-Fi routers. So we have enough Wi-Fi routers in the field that are capable of 300 megabits that can all be reflashed to OpenWrt or DDWrt or some other firmware, modern firmware that has not only this modern code but support for IPv6. However, incentivizing everyone here to go and reflash their routers with something real is still kind of a nerd thing. I had honestly hoped that in the generation of software went by, it started in 2012, that by 2016 most routers would already have this code. You wouldn't have to actually do it. Eero, there's dozens and dozens of commercial manufacturers that are shipping this stuff. But the ISPs themselves were basically buying the cheapest possible product and keeping it running for the longest possible time. So I'm happy about the L4S project. I'm happy about a whole bunch of WISPs.
Maybe I missed the motivation. Why would I want to do that? What would I get out of it? Oh, sorry.
Well, why would you want to flash your own router?
Yeah. What do I get out of it?
Friends don't let friends run factory firmware. Factory firmware is so insecure and so under-maintained that that's my first motivation. I never buy I only buy stuff that I know I can reflash with OpenWrt, knowing that the security will be there. Secondly, SQM. Thirdly, IPv6. And fourthly, there's zillions of other features that you can make a router do. Ad blocking, for example. If you just get routers and reflash them, the internet gets a lot better for you. Anybody else?
How does signal loss in Wi-Fi impact congestion control?
Okay. Thank you. Where did we get that one? In this wonderful book, this is Toki Oyland Jurgensen's PhD thesis, there is a thing called ending the anomaly. I have been working in Wi-Fi since 1998. I like to think, I don't like to think, but some of it's my fault. Wi-Fi has an interesting property. It's called the inverse square law. So where if you're standing right next to the access point, you might be able to get a gigabit. But if you're 4 feet away, you might be able to get 500 megabits. And if you're 8 feet away, you might get 250. And if you're 20 feet away, you might be lucky to get 20. So when signal loss, you need a certain amount of buffering, just a certain amount of buffering in order to make sure that data can get out to you at a gigabit. But that amount of buffering is so much bigger than what it needed to be at 20 feet on your front porch. So we applied the FQ-Cottle algorithm, solving what's called the Wi-Fi performance anomaly. We managed to speed up Wi-Fi under congestion by, we went from 10 seconds down to 40 milliseconds for most of our tests. And that, too, is part of the Linux kernel and part of about 9 Wi-Fi chipsets now, including Eero and a few others. So very proud of that day. That was a really awesome day, by the way. I'd struggled with this for years where you had, as soon as you moved far enough away, your network got weird. And it doesn't have to get as weird as it gets. So take a look at ending the anomaly and drool over the graphs for that.
I have a couple of questions about, I think it sums up to this one. Can you talk more about setting changes that can be applied to home routers? Is this on your website somewhere?
Not sure how to answer that. Most of my work has been in the OpenWrt world. There's a lot of subsequent work like DDWrt and stuff like that. So that's where I would look for config stuff. If anyone cares, the Wi-Fi router I recommend most is an MT79 from GL-INET 6000 series. There's a build there that has all the latest and greatest stuff. The goal in life is to be able to do Twitch gaming over Wi-Fi at distance. And we are succeeding in that now.
Question, you mentioned the backbones and Comcast, but in years past especially, the ISPs dramatically overloaded their network, right, and caused all kinds of problems, as well as the exchange points, like the Equinixes and such of the world. Are those problems pretty much solved, or are we still seeing a lot of that?
It's always DNS. There's a fellow by the name of Jeff Houston who's talked about how the internet has evolved. He works for AppNic. And by building out the CDNs to where we are basically a one-hop network now, all the content you might ever want is just one hop away from your ISP. So I like to think that the various and sundry failure modes that we had are mostly gone now. We have more than enough bandwidth along the backhaul for content. Where we're still falling down is on interactive traffic, video and voice and gaming. So it's my hope. I still see backbone routers way over provisioned. Cloudflare has a habit of leaving theirs at a default, so if they actually run out of bandwidth, they've got 400 milliseconds of buffering on their network, and it bugs me.
More questions?
I am hoping to do a song.
So, how does FQCoddle and hardware offload work?
That's a hard one. Okay, hardware offloads have appeared for FQCoddle on several devices today. We have not seen a lot of it recently. As happy as I am with FQCoddle as an algorithm, the power of it everywhere, it is not easily applicable to hardware. There's another one called Pi, which is what Comcast is using, which is slightly easier to pour into hardware. So I do hope that we'll see active Q-managed technologies appear directly in hardware. But these days, it's just pure BQL and software these days. Anyone else? I wrote a new song. The AIs have really been bothering me. I'm getting old. I'm having grave difficulty accepting this. And I hope that you all can help me sort it out. There's something happening here. What it is exactly clear. There's a man with a manifesto there. He's telling you, I got to beware. Saying, stop, baby, log off now. Get outside and get on down. The AIs hear every tweet, and they know you are what you eat. And your Kindle logs every page. I turned off mine. Turn to the days of rage. Oh, stop, baby, log off now. Get outside and get on down. Signal knows who you call, and they say they hear nothing at all. But Zoom is a bit more crass. Oh yeah, we spy, but only on the lower class. Oh, stop, baby, install Galen, and run your code on your own machine. Oh yeah, paranoia, it strikes deep. Into your arms it will creep. And sometimes I think I made a new friend, and she turns out to be an LLM. Oh, stop, baby, log off now. Get outside and get on down. Just stop.